Good afternoon, this is Sean McBride, and I want to give a quick update on some of the work I've been doing in the Chord gRPC project. I have just put together essentially the mother of all pull requests, and unfortunately my teammates have to review that. So I want to take a little bit of time and show the functionality I added and talk through some of the code choices I made. So first, I want to start here in Docker Compose because a lot of the work I've been doing has been centered around the idea of making it easier to scale up our Chord distributed hash table. So we have a couple of services here. The first is node primary, and one of the core ideas of a peer-to-peer service is that a node can basically join the cluster by contacting any other peer. That means there's really no difference between like a server and a client. But the complication with that for some of these orchestration scripts is you have to have at least one node that you have at a known location that other nodes can reach out to. And by default, most of these scripts assign basically kind of random hashes as the host names when the containers get spun up. So first I stand up one node with basically a pinned host name, node primary. And then that gives me enough information to tell all the other nodes that I dynamically start up, like how to reach that initial node. So that affects some scalability because we're obviously hammering this one node with a bunch of requests to join the cluster. But it works for this point of view. So we have these two things that they're really functionally the same. It's just this one node is pinned. This is basically a dynamic host name. And then we have basically a web app here. And the web app is composed of essentially a crawler that crawls the overlay network of the distributed hash table and gradually accumulates the state of the entire cluster and then displays that out in a data visualization, and which is somewhat interactive also. I'll show that in a bit. So that's everything here in this file. I want to go ahead and talk through the nodes because that's where I've been doing most of my work. So previously, all of the node logic was in one monster Node.js script, and I think it was like 1,800 lines or something like that. And so now it's broken out quite a bit more. And I also have reorganized the logic to try to break out the code that's specific to our application, which is basically a user service that stores user profiles in the underlying framework that implements the core Chord algorithms. So here in this Node.js file here, this is basically our entry script to start everything. And this basically just takes the arguments that are passed in from the command line, does some parsing on that, does some intelligence checking, including running a function here that makes sure that that known endpoint that we're trying to register with actually is something we can ping. So that just kind of rules out general network issues. Sometimes Docker can be a little strange with that. So we get our arguments, we validate that the endpoint we want to register with is available, and then we start up our service basically. And the way that we do that is we use our class called the user service, and we pass in our arguments. Then we call serve. Serve then tells that node to basically act as a gRPC server, and that allows it to field requests. And we want that to be up and available before the node then reaches out to the cluster. So after serve is up, then the user service calls join cluster, and that's when the node actually reaches out to that known node address that we validated earlier, and we build out the logical overlay structure of the DHT. So we can go ahead and take a look here at user service, just here. User service is a class, and we are extending Chord node. Chord node is the class where I've put all the general state and functionality associated with the Chord algorithm. And so this user service basically has the data API behavior on top of that. And so we have here a basically user map hash table in memory, and that stores the bits of the data of the user service that this particular node is responsible for. We can see here the serve behavior, which stands up the gRPC server and then exposes a bunch of methods, either that this class implements or that it inherits from the parent Chord node class. Yeah, and then we basically have the things that you do with users: fetch, remove, insert, stuff like that. So I think that's all pretty clean cut. So now we can click through and look at the Chord node parent class. And so the Chord node parent class is kind of what I would describe as our library here. Ideally, this should be structured in a way where if anyone wanted, they could take this library and then build a peer-to-peer application on top of our base functionality. I think we definitely have some work to do on the API to make that a little bit more possible, but we're, I think, on a reasonable track here. Some of the error correction here is also redundant with what we've done earlier in the application. And that's just because I think it's important to make sure that the library component also checks that, because this could be reused. And then we have the kind of the core state for a node in a THT. And one thing to just mention here about JavaScript. So with JavaScript classes, you don't currently have the ability to just add attributes like, host or whatever. You might see something like that. It's in other languages or whatever. You basically have to decorate this object with the attributes inside the constructor. And that's changing in the latest version of JavaScript, but it's not quite here yet. If we were to use TypeScript, we could add that now, but that just would take more time than it's worth. So here we're adding all the different state: the host, the port, that's basically where this particular node is living on the network, how it can be reached, the known node and the known host and the known port. That's the network location of the node on the network that we're trying to connect to when we join the cluster. And here we basically have default behavior that says, if the user didn't pass these in, let's assume that this node that we're standing up is the first node in the cluster. And so our known node, so the known host and known port, is really ourself. So we just copy our own host and port in. So then we've got our ID. The ID is basically the name, logical location of this node within the DHT namespace, which is plumbed out by our hash function. We have our finger tables, which is basically the performance improvement that allows us to take shortcuts along the overlay network. We have just general state about our predecessors and successors. Yeah, so then we just have just a heck of a lot of functionality in here. I've made some changes to some of this. Some of it probably still could be cleaned up a bit. But yeah, it's just a heck of a lot of code. And we do have a good amount of code commenting, and error checking. So that adds a lot to it. So currently the library files over 1,000 lines still, even after kind of breaking things out. Yeah, probably could organize it a little bit better, but I think it's okay for now. So that's, I think, pretty much everything in here. Maybe it's worth talking about the Utils library. So I basically have taken some of the constants that are used in several files and put them in here, and I export them from this utils file. We also have kind of common functions in here. computing the hash and whatnot. One other major piece of functionality that I added was a function that basically does centralized gRPC error handling. So it checks the particular error code of the gRPC error and then logs to console with helpful error messages. So I thought that cleaned up the console quite a bit and made it easier to debug. And then I also added this connect function. And that's just because we had this kind of caller syntax all over the place. And we're basically accessing this in the same way, and we're always accessing the same sort of gRPC server since we're peer-to-peer and we're all kind of the same thing. So I thought just go ahead and centralize this and make it a little simpler. Yeah. So I guess I'll go ahead and start the application and show you what it kind of looks like. So I can start the app. Actually, no, before that, let me show debugging. So with Visual Studio Code, there's a visual debugger tool, which is this thing here. It looks like a bug. You click on it, and we have some options here. Launch via npm. This should be something that's added into the repository. So if you check out the project and start the application, you should get this option. And if I click this here, what it does is it launches a new package.json script called debug, which starts basically our first node in the cluster and exposes a particular port that communicates with Visual Studio Code to be able to provide that kind of rich debugging functionality. So now if I hit launch with npm, and of course I just apparently have broken this. Let me just go ahead and click in here to see what the heck's going on. I probably refactored something and messed something up here. Okay. Chord app node. '69 host port. Right. Okay. Args. Sorry about that. This used to be in a separate function, and I inlined that because I was only using it once. So args.host, args.port. Okay, I think that should do it. So let's try that again. Okay, cool. So now we're running, the debugger is attached. And this is pretty neat because I can insert breakpoints into the editor and then take a look at whatever the state of the application is at that particular debug point. So let's imagine, for example, that I have a bug in the code to insert a user. I can go to user service. I can go to insert user, I think here. And I can insert a breakpoint. And you do that by going to the line here, like 145. Here's the red dot. You click on it. And now we have a breakpoint. You can also see that down here. So if I go to my terminal and I now use the client to try to insert a user. Let's see. There we go. On the server, it received the request and it triggered the gRPC handler, which then brought us to here. And so now this is basically frozen. The client is frozen, and we can see the in-memory state of what's going on here. So since we are now using object orientation, a lot of the state is contained under this, which is, you can see, is an instance of user service. So if in here we've got our finger tables. We've got our local host, known host, predecessor, successor, user map. It's currently empty. Hopefully we were going to add something here. So now we're in the program and we have these different commands here. If we hit this continue button, basically that says just run wild after this. So the thread of execution will continue after this line and keep running. And since our only breakpoint is here, we don't have any other breakpoints, we'll just basically run real time and see a response here. So I guess I can show that. So user inserted successfully. Okay, now let's imagine we want to test that if someone tries to insert the same user, or with the conflicting user ID, that we handle the error correction. I can do that by running client again. We're going to hit the same breakpoint here. And this time we can see that unlike before, the user map actually has the user inserted with all the correct details. And now we actually want to use these. So step over basically means you want to advance in the current basically block of code. Step into means you want, if you're on a line that has a function invocation, you actually want to step into that function you're invoking, and then you'll jump into that function and step through that. If you do step over instead, you will basically advance and then get the return value of that function and stay within the same scope. Step out is useful if you step into a function and you just want to check a couple of things, and then you want to go out to your caller, the function that called you. You can hit that and jump back out. So that's kind of the debugger 101. So for this situation, we can do step over, and you can see this kind of line here that we're advancing. And as we're advancing, you could see that this updated. So this user got populated here. We can advance again. Okay, so now it looks like here we check to see if this was edit, and we see edit was set to false. So this is an insert. And so now we can take a look at this if block here. So if user.map contains user ID, and we can see we're trying to add user ID 5. And if we look inside of our user map, we see we already have 5. So this should be true. And then we want to check, are we not in edit mode? Because if we're in insert mode, we should just return a code that a gRPC code that says it already exists. So we would expect to basically drop into here and then return this gRPC code 6 to the client. Let's see if that happens. Yep, so we entered the scope. We're going to return. And so now basically I can hit continue and we get the message user already exists here. So that's cool. That works as expected. So that's how the debugger works. Generally, if you're hitting an error, you can basically run the node like this and put a breakpoint on an intelligent spot. If you're trying to test more of the clustering functionality, you can actually spin up another node here using basically these commands. So our debug node is on localhost port 8440, so any of these should work. Known host is not defined. And of course, I've got another bug here. Oh, great. And it's the same issue as before, basically. Gosh, I need more attention to detail here. So args.knownhost, args.knownport. And let me just go ahead and check the rest of this function here to make sure I'm not doing the same stuff anywhere else. Okay, args. Okay, I think that's good now, so. And I probably crashed out my debug server because of that other issue, so relaunch that. Let's see, what am I missing here? Okay, so let me check the package JSON. Debug, I'm running on localhost port 8440. Right. Okay, and then here, I'm trying to run 8441 and connect 8440. Unable to connect. Yeah. Goodness, this is interesting. Okay. Well, let me stop this, restart it, and see if that makes a difference. Okay. Geez, I am just super befuddled here. I don't know. I'll have to take a look at this a little bit more. But yeah, let's go to the demo, and then that'll help figure out if this has to do just with the debug mode or if that's something else. So close this out. So now, theoretically, remove the breakpoint. I should be able to do this. Docker compose up, scale, node secondary 10, detached, and let me do a build just to make sure I'm hitting any errors if they exist. Okay, so everything's starting up. So if I go to this address, here's our data viz. I added basically a number here to signify the number of nodes in the cluster. And yeah, it looks like they're able to connect with each other, so I must have something messed up with my debug arguments or something like that, or a local machine issue. So we should have 11 in total, 10 secondary plus 1 primary. There's a chance of a occasional node collision, which could be what happened with that 11th. Okay, right, and same as before, you can click on any of these and see details over here in the detail pane. Okay, so let's assume that that one is a goner, and let's increase this number to something ridiculous. Scale up to 30, and let's kind of see what happens here. Okay, there we go. it can take a little bit for these to kind of appear, especially when a bunch of them join at once. Going from 10 to 30 simultaneously is quite a bit in one go. So if you got 10 out of 11 last time, I wonder about this time. It's kind of fun and organic to watch these settle out. Yeah, so that's 28 out of 31. I mean, it's probably about as good as we might get. We might have one or two more kind of pop in a little bit sometimes. It seems like some of the nodes take a little while to kind of stabilize. Yeah, so that's basically the state of the project here. And one other thing I've noticed is when we have just a ton of nodes like this, if we then use our data API, things are crazy slow. So like here, we showed this command earlier. It was almost instantaneous with just the one node up. But now if we run it, it's going to basically hang here for a minute or something like that, which is a little bit of a bummer, but it does eventually. Oh, there we go. I guess not a minute, a little bit quicker. And so let's try to see if we can look that data back up. This part seems to take a little bit longer. Yep. Who knows? I had left this and had it sit for like a minute or 90 seconds before, and it never really totally resolved. But I don't know. Definitely worth doing some debugging on. So I think that's pretty much everything. Let me know in Slack if you have questions. And otherwise, I feel like we're gradually getting there. And if you feel like the pull request is an improvement, I think would definitely be worth merging. My hope is that the cleaner structure combined with the debugger functionality makes this a much firmer foundation for us to kind of work on and knock out the last couple of issues to get this whole thing done. And I otherwise really appreciate all your hard work this past semester. And I thank you for your forbearance as I push a bunch of changes into this one massive BR. All right, later. Bye.